How can a black hole, an object from which nothing escapes, somehow return everything it has swallowed? I often find myself returning to that question. It sounds like a paradox, crafted for a philosophy classroom, yet it sits at the center of modern theoretical physics. In the 1970s, Stephen Hawking used quantum theory to argue that black holes emit radiation. If they radiate, they shrink. If they shrink, one day they disappear. And if they disappear, then everything that fell into them must somehow be accounted for. But Hawking's own calculation appeared to erase information entirely. That was the puzzle. It still is. I remember speaking about this recently and pointing out something mildly uncomfortable for many of us. Hawking might have been wrong about the most crucial detail. His mathematics was brilliant, but the conclusion that information vanishes from the universe seems increasingly unlikely in the light of new work. My mind often drifts back to the moment I first saw the image of a black hole produced by the Event Horizon Telescope. It was familiar in a strange way, a blurred ring of light bent around a shadow, exactly as general relativity had predicted for more than a century. And yet, there was something almost impossible about it. A photograph of a place where space-time curves so steeply that all paths lead inward. Let's begin. I have always thought that some of the most profound shifts in physics begin with the simplest questions. In the 1970s, Stephen Hawking asked one that still shapes the way we think about the universe. What happens to the things that fall into a black hole? It sounds almost naive, a question a curious child might ask. But it opened a path that led straight into one of the deepest paradoxes in science. To appreciate the weight of that question, imagine a black hole not as a cosmic monster, but as a region of space-time where gravity curves so sharply that every possible path points inward. Once matter crosses the event horizon, it is carried inevitably toward the interior. In Einstein's general relativity, this inward pull cannot be resisted. It is not a force, it is the geometry of the universe expressing itself. For decades, physicists were comfortable with a simple picture. Anything that fell in stayed in. A black hole was, in essence, a one-way journey. But Hawking approached black holes using the tools of quantum theory. When he analysed the behaviour of empty space near the event horizon, or what we normally call vacuum, he found that it could not remain quiet. In quantum mechanics, the vacuum teems with fleeting pairs of particles that appear and disappear too quickly to be observed directly. Hawking realised that near the horizon, one of these particles could escape before its partner vanished. When that happens, the escaping particle becomes real, carrying a tiny amount of energy away from the black hole. This outward trickle is now called Hawking radiation. It is extraordinarily faint for astrophysical black holes, far too faint to detect with present-day instruments, but its conceptual significance is enormous. A black hole that radiates must lose mass. A black hole that loses mass must shrink. And a black hole that shrinks must eventually evaporate. Hawking followed this logic to its conclusion. If a black hole disappears, then whatever fell into it, stars, planets, atoms, or information itself, must be accounted for. But his own calculations suggested something troubling. The radiation emitted by the black hole carries no imprint of what formed it, or of what later fell inside. It is what physicists describe as featureless. The radiation contains energy, yes, but no information about the identity of anything that contributed that energy. It is simply thermal, like the faint glow of a warm object. And here lies the central tension. In quantum mechanics, information cannot be destroyed. That is not a philosophical preference. It is a fundamental requirement of the theory. If you take a book and burn it, a mundane example often used in discussions of the paradox, the letters vanish, the pages curl, and the smoke disperses. But if you could collect every particle of ash, every photon of light, every molecule of gas, and if you had perfect knowledge of them all, you could, at least in principle, reconstruct the contents of the original book. Nothing has been lost. The information has merely been transformed. Hawking's calculations seem to violate this principle. If the radiation contains no information about what went into the black hole, and if the black hole eventually evaporates completely, then the original information is erased from the universe. In every other context in physics, this simply does not happen. What makes the issue even more striking is where the paradox arises. One might expect such a conflict to appear deep inside a black hole, near the singularity where our current theories fail, but that is not the case. Hawking's paradox emerges at the horizon, a region where the curvature of space-time can be relatively mild for large black holes, and where the laws of physics should be reliable. It is this detail that makes the paradox so important. The problem shows itself not at the extremes, where theory breaks down, but in a place where our theories should work together seamlessly. When Hawking presented his results, the physics community was split. Some took the view that information might truly be destroyed, that black holes were the only erasers of information in nature. Others suspected that something subtle was missing from the calculation, something that future insights in quantum gravity might reveal. Over the decades, the problem grew into one of the central challenges of theoretical physics, precisely because it forced two pillars of modern science, quantum mechanics and general relativity, into conflict. As I reflect on Hawking's original question, I'm struck by how much it reshaped our understanding. A single, almost innocent query led physicists to reconsider the nature of space, time, and information. It encouraged the search for a deeper framework, a theory capable of reconciling the quantum world with gravity. For us tonight, this chapter serves as a foundation. We begin with a question about the fate of falling matter, but we soon find ourselves discussing the architecture of the universe. Hawking radiation, the behavior of vacuum near the event horizon, the idea of information conservation, these are not separate pieces. Together they form a path that leads directly into the heart of the black hole paradox. There was a moment in recent scientific history that felt quietly transformative to me. It happened in 2019, when the Event Horizon Telescope collaboration released an image of a black hole in the galaxy M87, a system 55 million light-years away. The image wasn't sharp in the way we might expect a photograph to be. It showed a ring of orange light with a darker circular region at the center. Yet behind that blurred glow lies one of the most extraordinary achievements of modern astronomy. A picture of space-time itself responding to gravity in precisely the way Einstein predicted more than a century ago. To understand what we are looking at, it helps to remind ourselves of a simple fact. We never photographed the black hole directly. The interior of the event horizon emits no light. Nothing can escape from within that boundary. What the EHT reveals is the shadow, the silhouette carved out by space-time geometry, surrounded by radiation from matter spiraling around the hole at tremendous speeds. This matter forms what astrophysicists call an accretion disk, a thin, hot ring of gas and plasma heated to extreme temperatures as it orbits. The glow comes from this disk, but the shape of the ring, the asymmetry of its brightness, and the darkness at its center are all consequences of general relativity. Gravity bends light, so photons from the far side of the disk curve around the black hole and reach us from unexpected angles. In effect, the black hole creates a natural lens. The EHT image captures this bending of light, producing a circular silhouette larger than the physical event horizon. When I first saw the image, I remember thinking how remarkable it was that the shape looked so familiar. Not because we had seen it before, but because the theory had predicted it so clearly. The EHT EHT uses a technique called very long baseline interferometry, combining radio telescopes across Earth to form a virtual instrument the size of the planet. This enormous effective aperture gives us the angular resolution needed to observe something as small as the silhouette of a black hole in a distant galaxy. The precision required is astonishing. Each telescope must synchronize using atomic clocks accurate to a few billionths of a second. Massive volumes of data are recorded on hard drives and shipped to central computing facilities where they are combined to reconstruct the image. Even with all of this, we do not literally see the black hole. We infer its geometry from the radiation around it. Shortly after the M87 image came the second major result, the first picture of Sagittarius A Booz, the supermassive black hole at the center of our own galaxy. This one is much smaller, only a few million times the mass of the Sun, but it posed a greater challenge. Sagittarius A changes rapidly. The matter around it shifts on timescales of minutes, making it difficult to reconstruct a stable image. Yet the EHT succeeded, and the result is another ring, another shadow, another confirmation that space-time behaves exactly as predicted. The striking thing is that these images match simulations of general relativity with impressive accuracy. Long before the photographs existed, researchers used Einstein's equations to model how light would behave near a black hole. They produced synthetic images showing a bright, lopsided ring with a dark interior. The observed images lie almost exactly on top of those predictions. To me, that alignment is quietly beautiful. It means that across vast distances and through immense complexity, gravity follows a pattern that human mathematics can describe. When I talk about these images, I often notice a tension between their simplicity and their depth. At first glance, they look almost abstract, a blurred circle on a black background. But that circle represents the closest we have come to visualizing an object that defies ordinary intuition. We are looking at the boundary between what can communicate with the universe and what cannot. We are seeing light that has struggled through gravity, its path distorted and stretched before reaching Earth. And we are glimpsing the shadow of a place from which light will never emerge. There is also a personal dimension to this discovery. I remember the first time I saw the M87 image projected onto a large screen. The room fell silent in a way that only scientific clarity can produce. It wasn't noisy excitement. It was a recognition that something profound had become visible. For more than a century, black holes were mathematical constructs, powerful, elegant, and mysterious. Now we could point to the sky and say, there it is. These photographs are not just aesthetic achievements, they are essential clues in the effort to understand Hawking's paradox. The shape of the shadow, the size of the ring, and the distribution of brightness all tell us about the structure of space-time outside the event horizon. They show that general relativity works with extraordinary precision in this region, the very region where the paradox arises. If the horizon behaves exactly as the equations predict, then the conflict between general relativity and quantum mechanics must be resolved not by adjusting the classical description, but by discovering something deeper. There is something strangely understated about the event horizon. People often imagine it as a surface of fire or a violent boundary. In truth, it is nothing more than a location in space-time, a place where the outward direction tilts so steeply inward that all possible paths lead the same way. If you were to drift toward a supermassive black hole, the kind we find at the center of galaxies, nothing dramatic would happen as you crossed the horizon. No sudden change, no warning. The fabric of space-time would simply carry you across. From your own perspective, the fall would feel uneventful. Your clock would continue to tick 1 second per second. The horizon would not appear as a barrier. It would not appear at all. General relativity makes this very clear. For a sufficiently large black hole, the tidal forces at the horizon are gentle. You could cross it without noticing. And if the black hole were millions of times the mass of the Sun, you might have 30 hours or so before reaching the singularity, the place where Einstein's equations predict an end of time. Observers who remain outside see something entirely different. They watch the infalling object slow down. The colors stretch, the motion freezes, the final moment hangs forever just above the horizon. From the outside, time appears to stop at that boundary. This divergence between perspectives caused real confusion in the early decades of black hole physics. Some physicists argued that nothing could cross the horizon because, from their viewpoint, the passage took an infinite amount of time. But general relativity teaches us that reality is shaped by the observer's path through space-time. Time can stop from one vantage point and pass normally from another. Understanding this duality helps clarify why the horizon, rather than the singularity, is the stage on which Hawking's paradox plays out. The singularity remains hidden behind the horizon. The physics there is beyond our current theories. The curvature becomes so extreme that the mathematics of general relativity breaks down. We do not know what happens at that ultimate endpoint, but the paradox does not depend on the singularity. It emerges in the region around the horizon, where space-time curvature is modest enough that Einstein's equations should be completely reliable. When Hawking analysed the quantum vacuum near the horizon, he found that it cannot remain empty. Quantum field theory predicts that pairs of particles flicker into existence everywhere in space. Normally, they annihilate each other almost instantly, leaving no observable effect. But near a horizon, one member of the pair can fall inward while the other escapes. The escaping particle becomes part of the Hawking radiation. The partner that falls in carries negative energy, not in the colloquial sense of being less than zero, but in the precise sense that it reduces the mass of the black hole over immense timescales. This imbalance leads to evaporation. Here is where the tension appears. The radiation that escapes originates from the vacuum, not from the material that fell in. It carries no information about the identity of the star that collapsed or the particles that crossed the horizon later. It is thermal. It has no structure that could encode the details of the infalling matter. If this picture were complete, information would simply vanish from the universe. That conclusion contradicts the foundations of quantum mechanics, which insist that information is preserved in every physical process. Physicists found this deeply unsettling, not because of aesthetics, but because the mismatch occurs in a region where both theories, quantum mechanics and general relativity, should be trustworthy. At the horizon, the gravitational field is strong but not extreme for large black holes. The curvature is gentle. We have no reason to doubt our equations there. And yet, the combination of those equations leads to a contradiction. The horizon, therefore, becomes more than a boundary. It becomes a diagnostic tool. It is where we test our deepest principles. It is where we can observe the tension between two theories that normally coexist peacefully. The paradox forces us to consider whether the horizon behaves differently than we assume, or whether quantum theory has some subtlety we have not yet discovered. Perhaps the information is not lost, but encoded in a way we do not yet understand. Perhaps the radiation contains correlations too delicate for Hawking's original calculation to reveal. Or perhaps space-time itself has a structure that reorganizes information in a way our current tools cannot describe. When I think about this, I often return to the quiet simplicity of the EHT images. The ring around the shadow is a direct signature of how space-time curves near the horizon. It behaves exactly as general relativity predicts. The geometry is not hinting at an error or a failure in Einstein's theory. It is the quantum side of the story that remains incomplete. The horizon does just what the equations demand. But the information paradox tells us that something remains missing from the deeper description. Something curious happens when you ask what it truly means to fall into a black hole. You realize the question does not have a single answer. The story depends on who is watching. Two descriptions unfold, each internally consistent, each derived from well-tested physics, and yet they cannot both be complete in the same way. This tension lies at the heart of what became known as black hole complementarity. If I imagine you drifting toward a supermassive black hole, the kind with millions of solar masses, your experience is quiet. You feel no sudden pull, no violent distortion. General relativity tells us that for large black holes, the tidal forces near the horizon are mild. Your clock keeps ticking. You speak normally. You continue forward, carried by the flow of space-time. The horizon does not appear as a surface. It is simply a place you pass. And once you have stepped beyond it, all paths through space-time point inward. You move toward the singularity in the same way you move toward tomorrow. Not because you choose to, but because the geometry of space-time defines your future. Yet a distant observer would describe something profoundly different. From their vantage point, you slow. Your signals stretch toward longer wavelengths. Your image becomes dimmer. You appear to hover, suspended just above the horizon, taking an infinite amount of time to fall in. This picture also emerges cleanly from Einstein's equations. Nothing in their mathematics suggests that the outside observer is mistaken. Their clocks tick at a steady rate. And according to those clocks, you never quite cross the boundary. Two observers, two clocks, two incompatible stories, and yet both arise from the same theory. This duality becomes even more intriguing when quantum mechanics enters. Hawking's calculation depends on the viewpoint of the distant observer because the radiation he derived emerges from the horizon as seen from the outside. From that perspective, the horizon behaves like a hot surface, leaking thermal radiation into space. And in that description, anything trying to cross the horizon is effectively destroyed, burned in a sense, as the information it contains is washed into the outgoing radiation. But your own experience says nothing of the sort. You fall freely, no flames, no resistance, nothing to mark the transition. You continue inward until the geometry forces your world lines to converge. These two views cannot be simultaneously observed, but they can both be internally true. That is the essential idea behind black hole complementarity, developed by physicists such as Leonard Susskind and Gerard 't Hooft. The argument goes like this. No observer can access both perspectives at once. You cannot hover outside a black hole indefinitely and also fall into it. You must choose one trajectory, one frame of reference. Physics only demands that each observer see a consistent story, not that these stories can be stitched together into a single shared narrative. Complementarity is not invoked out of philosophical fancy. It is a consequence of how relativity and quantum mechanics assign meaning to measurement. If information can only be defined relative to an observer, then contradictions between frames may not be contradictions at all. They may simply reflect the fact that what happens depends on the path through space-time taken by the one who observes it. Even so, complementarity alone does not resolve Hawking's paradox. It suggests that the inside and outside descriptions need not agree, but it does not explain how information avoids destruction. For that, we need something quantum, something encoded in correlations too subtle for the classical picture to show us. The puzzle becomes sharper when you consider that the horizon is the location where the rules appear to clash. The infalling observer sees empty space. The outside observer sees a hot surface. Both cannot describe the same physical degrees of freedom in the same way. The mismatch tells us that the horizon cannot be a simple classical boundary. It must have structure, or it must reflect some deeper principle we have not yet uncovered. Thinking about these conflicting pictures always reminds me of how often physics forces us to re-examine our assumptions about objectivity. We tend to imagine that events have a single definitive story, yet the universe sometimes refuses to conform to that expectation. In curved space-time, the notion of simultaneity dissolves. Observers disagree about time. In quantum theory, measurement shapes the behavior of systems. And around a black hole, these two ideas meet, overlap, and challenge the classical assumption that reality must be the same for all. There is a quiet fascination in sensing how close these questions bring us to the limits of understanding. Black hole complementarity does not claim to be the final answer. It functions more like a guidepost. It tells us that if information is preserved, as modern work increasingly suggests, then the horizon must participate in the accounting in a way we do not yet fully understand. It points toward quantum entanglement, correlations, and the non-local structure of quantum fields as possible ingredients. By the time Hawking introduced the idea of evaporation, he had already forced physicists to grapple with these dual viewpoints. But it was the paradox, the claim that information disappears, that made the need for a deeper explanation unavoidable. It is worth pausing to appreciate how radical Stephen Hawking's insight was when he first produced it in the early 1970s. Until that moment, black holes were understood almost entirely through Einstein's general relativity. They were meant to be cold, silent regions of space-time, absorbing everything that crossed the horizon and emitting nothing in return. The mathematics of relativity treats them as perfect one-way traps. Once you move inside, your future ends at the singularity, and nothing you do can send a signal outward again. Hawking approached the problem using a different lens: quantum field theory. Instead of treating space-time as a passive backdrop, quantum theory treats even empty space as full of activity. The vacuum is not a void. It seethes with fluctuations, tiny momentary excitations that appear and disappear too quickly to be measured directly. These fluctuations are not speculation. Their effects have been measured in laboratory experiments such as the Casimir effect, and they are built into the modern understanding of particle physics. What Hawking did, in essence, was ask how these quantum fluctuations behave near the event horizon of a black hole. And the answer surprised everyone. When he calculated the behavior of quantum fields in such an extreme curved space-time, he found that the horizon behaves as if it emits radiation, not because anything is escaping from inside, but because the structure of the vacuum itself is disturbed by the presence of the horizon. A simple picture often used to communicate the idea goes something like this. Imagine the vacuum producing pairs of excitations, one with slightly more energy and one with slightly less. Near the horizon, the geometry can separate them. One member of the pair escapes outward, while the other falls inward. To conserve energy overall, the black hole must lose a tiny amount of mass. Over immense spans of time, a black hole radiates, shrinks, and eventually disappears. This picture is not literally accurate, but it captures the intuition. The radiation emerges from the vacuum outside the horizon, not from the interior. This is the crucial point. Because the radiation does not come from the material that fell in, Hawking argued that it carries no imprint of the original information. Every bit of radiation looks the same, a featureless thermal glow, like heat radiation from a warm object. In thermodynamics, such radiation does not encode the microscopic details of whatever produced it. It is just heat. Here is where the paradox begins. Quantum mechanics teaches that information cannot be destroyed. Even if a book is burned and reduced to ash and light, the arrangement of atoms and photons still contains, in principle, the information about the contents of the book. It would be unimaginably difficult to reconstruct, but the underlying laws do not erase it. Hawking's radiation, however, appeared to erase information completely. If a black hole evaporates entirely, leaving only this thermal glow behind, then the universe loses information. That would mean quantum mechanics, one of the most accurate and experimentally verified theories ever developed, would break down at the horizon. It is striking that this problem arises not at the singularity, the region we do not fully understand, but just outside the horizon, where space-time curvature is modest, and our theories should be reliable. Hawking performed his calculation in a region where the gravitational field is not extreme. That is why the paradox carried such weight. It did not rely on speculative physics. It emerged from a combination of general relativity and quantum mechanics, precisely in the regime where both should work. When I think about the elegance of Hawking's calculation, I find it remarkable that such a profound contradiction could arise from ingredients that appear so straightforward. Einstein gives us the geometry. Quantum theory gives us the vacuum fluctuations. Combine them carefully, and you find a result that seems to violate one of the most fundamental principles of physics. Scientists spent decades trying to understand where the reasoning might have failed. Was the problem with the idea that black holes emit perfectly thermal radiation? Was there some subtle correlation hidden within the radiation that Hawking's calculation could not detect? Or was something deeper required, a new way of thinking about space-time itself? This question drove much of the theoretical research of the late 20th century. The paradox became a beacon. It guided work in string theory, holography, quantum information, and the effort to merge general relativity with quantum mechanics into a single consistent framework. In the end, the paradox persisted because Hawking's reasoning was too compelling to dismiss. His calculation used tools that had proven reliable in every other context. It was not the kind of result one could wave away as an artifact of approximation. It demanded an answer, and that answer began to emerge only in the last few years through a combination of ideas from quantum information theory, gravitational path integrals, and the geometry of entanglement. The modern view, increasingly supported by detailed calculations, is that Hawking's conclusion was incomplete. Black holes do radiate, and they do shrink, but the radiation does not remain featureless forever. As the black hole evaporates, the structure of quantum entanglement changes, allowing information to gradually reappear. The path to that conclusion is subtle, but its implications are profound. The paradox forced us to reconsider some of our most basic assumptions about space, time, and the nature of information. Every so often, I like to sit quietly and remind myself that the room around me is not as still as it appears. Space is stretching and contracting by an amount far smaller than the width of a nucleus, stirred by gravitational waves passing through the Earth. These waves come from collisions that happened millions or even billions of years ago. Black holes spiraling together, neutron stars tearing each other apart. And yet the disturbances reach us now. They alter the flow of time by a fraction so tiny that only extraordinarily precise instruments can notice. But they are real. They ripple through you, me, and everything else. Gravitational waves were predicted by Albert Einstein in 1915, but for a long time they were considered unobservable curiosities. No one knew how to measure distortions so faint. A wave from a distant collision might stretch a 4-kilometer length of space by less than a 10,000th of the diameter of an atomic nucleus. The scale is unimaginable. And yet, physicists built machines capable of detecting exactly that. The Laser Interferometer, Gravitational Wave Observatory on LIGO, consists of 2 enormous instruments, one in Washington State and the other in Louisiana. Each observatory sends laser beams down two perpendicular tunnels, each 4 kilometers long. Mirrors reflect the beams back and forth. If space-time stretches along one arm and compresses along the other, the returning beams no longer line up perfectly. The interference pattern shifts by an amount so small it would be invisible to every ordinary detector. In 2015, LIGO observed such a shift. The signal matched the predicted shape of two black holes spiraling together and merging. It was the first direct detection of gravitational waves, and it confirmed that violent astrophysical events could indeed shake space-time in ways we could measure. Virgo, a similar observatory in Italy, soon joined in, improving the ability to locate sources on the sky. Since then, dozens of detections have been made: black hole collisions, neutron-star collisions, and combinations in between. Some of the black holes turning up in the data are surprisingly massive, 30 or 40 times the mass of our Sun, and sometimes more. Their abundance came as a genuine surprise. Before the observations, many astrophysicists expected such heavy black holes to be rare. Their presence hints at stellar histories more varied and chaotic than previously imagined. Detecting gravitational waves does more than confirm Einstein's theory. It gives us a way to probe regions of the universe where light cannot escape. When two black holes collide, the event releases no electromagnetic radiation. The merger happens in darkness. Only space-time itself carries the news. That is why gravitational wave astronomy is transformative. It reveals phenomena that were completely hidden before. These detections also provide a testing ground for general relativity under extreme conditions. The waves encode the shape of space-time during the final moments of a merger. By analyzing the waveform, its rise, its peak, its gradual fading, physicists can test whether Einstein's predictions hold. So far, every observation aligns with the theory remarkably well. But each new detection gives us another opportunity to search for deviations that might point toward deeper physics. When I think about these waves traveling across the cosmos, I find it helps to picture them as storms in time, a phrase Kip Thorne, one of the founders of LIGO, once used. A storm in air shakes leaves, a storm in the ocean lifts waves. A storm in time stretches and squeezes the intervals we call moments. It is an evocative picture, but the underlying physics is concrete. A gravitational wave is a change in the geometry of space-time, a literal alteration of distances and durations. There is an unexpected subtlety here. Even though the waves passing through you are unimaginably weak, they tell us something fundamental about the nature of space-time. It is dynamic. It can carry energy. It can oscillate. It can transmit information. That realization ties directly into the larger question of how gravity and quantum mechanics might fit together. If space-time behaves like a field, one that can vibrate and respond, then perhaps it has a microscopic structure, much like the quantum fields we already understand. Gravitational wave observations also provide indirect support for the idea that black holes must preserve information. When two black holes merge, the final object settles into a stable state, radiating gravitational waves in a pattern known as a ring-down. The details of the ring-down encode the mass and spin of the final hole. If information were truly destroyed in a merger, the constraints on these properties might differ from what general relativity predicts. So far, every measurement is consistent with information being preserved. As the detectors improve, with longer arms, quieter lasers and cryogenic mirrors, we expect to observe smaller distortions, fainter events, and a wider variety of sources. Future instruments like the Einstein telescope in Europe and the space-based LISA mission planned by ESA and NASA promise sensitivity far beyond what we have today. They will allow us to study black holes of entirely different masses, including the enormous ones in galactic centers. Listening to the universe through gravitational waves is unlike any other form of observation. It is not just light or particles striking a detector. It is the geometry of reality itself arriving at your door. I sometimes think about how long it took for the central puzzle of black holes to sharpen into something answerable. When Stephen Hawking first performed his calculation in the mid-1970s, he was working with the tools of quantum field theory in curved spacetime, a hybrid framework that treats matter quantum mechanically, but treats space-time itself as smooth and classical. That calculation was meticulous, and for many years it stood unchallenged. Black holes emit radiation that carries no imprint of what fell in. Information vanishes. Full stop. And yet, for decades, there was a quiet sense that something about that conclusion could not be the final word. Quantum mechanics does not allow information to be destroyed. It can be scrambled, diffused, or hidden in correlations, but not erased. The laws of physics preserve information in ways that are surprisingly strict. So, when Hawking's results said the opposite, physicists took it seriously. Not because they thought quantum mechanics was wrong, but because paradoxes are often where progress begins. A way to picture the issue is to imagine a diary thrown into a black hole. From Hawking's perspective, the radiation emitted by the hole, as it slowly evaporates, contains no trace of the diary's content. If you collected the radiation over unimaginably long times, you would find a smooth and featureless distribution. There would be no possible way, even in principle, to reconstruct a single sentence that had once been written inside. That is what information loss means. The universe forgets. The modern breakthrough came when a new generation of physicists revisited Hawking's original calculation with tools that did not exist in the 1970s. Quantum information theory had matured. Ideas about entanglement, correlations, and the structure of quantum states had become central to physics. And holography, the discovery that certain gravitational systems can be described by lower dimensional quantum theories without gravity, provided a way to translate problems about spacetime into problems about information. One of the most important insights came from Don Page, who in the early 1990s analyzed how the information content of radiation from a black hole should behave if information is ultimately preserved. He predicted a curve, now called the Page curve, that rises at first, reaches a peak, and then falls back to zero as the black hole completes its evaporation. In plain language, early radiation looks thermal, carrying no information. But later, radiation becomes increasingly structured, containing correlations that encode the details of what fell in. For a long time, no one knew how to derive the Page curve from gravity itself. It was a target, not a result. The challenge was simple to state. Show, using space-time physics, that information must eventually leak out. Around 2019, progress happened remarkably quickly. Several research groups found ways to include quantum effects of space-time itself, not just quantum fields living on top of it, in the calculation of the radiation. These new techniques introduced the idea of quantum extremal surfaces and islands, concepts that effectively track where information can reside when space-time geometry fluctuates quantum mechanically. In ordinary language, the idea goes something like this. If space-time is allowed to behave quantum mechanically, then the boundary between inside the black hole and outside becomes less rigid. The information that seems trapped behind the horizon can influence the structure of the radiation emitted far away. The radiation is not created in isolation. It is entangled with degrees of freedom that once lived deep inside the gravitational well. Over extraordinarily long times, this entanglement becomes the mechanism by which information escapes. When these ideas were combined, the Page curve appeared naturally from the calculations. It was no longer an assumption. It emerged from gravity itself, provided gravity was treated as a quantum system rather than a fixed classical backdrop. The consequence is profound. Black holes do not destroy information. The information is unimaginably scrambled, dispersed across correlations among vast numbers of emitted particles, but in principle, it is still there. If you had a quantum computer larger than a galaxy and timescales longer than the remaining lifetime of the universe, you could reconstruct what fell in. This conclusion doesn't mean Hawking's original calculation was wrong in the usual sense. It means it was incomplete. He assumed that space-time remained classical, smooth, unchanging. Under that assumption, his answer was exactly correct. But when quantum effects of space-time are included, tiny corrections that become important only after very long times, the story changes. What fascinates me is not just the resolution itself, but what it implies. To preserve quantum information, space-time must possess a hidden structure. It cannot be an inert stage on which physics unfolds. It must participate. The geometry of the universe has to store and release information in ways that classical general relativity cannot describe. That is why many physicists now believe we are glimpsing features of a deeper theory, one in which space-time is not fundamental, but emergent. There is a quiet elegance in the idea that information, the most intangible quantity we know, influences the shape and behavior of space-time. The resolution of the paradox hints at this. Information forces gravity to obey the rules of quantum mechanics. And that requirement may tell us how space-time itself arises from more primitive ingredients. When I think about it in that way, the paradox becomes less a problem and more a guide. It points toward the foundations. It suggests that the universe, at its deepest level, is woven from relationships, from entanglement, structure, and information flow. There are moments in physics when an idea first appears and feels almost too strange to take seriously, yet over time you begin to see it surface in different contexts, from different directions, until it becomes impossible to ignore. The notion that space-time itself, the three dimensions of space and the single dimension of time, might not be fundamental is one of those ideas. It doesn't begin as a bold claim. It begins quietly, as a requirement. Something is needed to make sense of what black holes are telling us. I often think back to Einstein's original insight. Gravity is geometry. His general theory of relativity describes how matter and energy shape the curvature of space-time, and how that curvature guides the motion of planets, stars, and light. It is an extraordinarily successful description, but Einstein never said what space-time is. He only told us how it bends. Quantum mechanics, in contrast, says almost nothing about geometry. It is a theory of information, of probabilities, entanglement, and correlations. When you combine the two frameworks, as black holes force us to do, their distinct languages begin to overlap. Geometry, the thing relativity takes as given, starts to look like something that can be built from patterns of quantum information. One of the simplest ways to imagine this is to picture entanglement, the deep connection between quantum systems that links their behavior even across large distances. Entanglement is not a force. It is not transmitted. It is simply there, a kind of relational structure. And it turns out that if you take many such relationships and arrange them in an intricate network, the resulting pattern can behave like a piece of space. You can measure distances within it. You can define surfaces. You can even reproduce the curvature that Einstein associated with gravity. This is not speculation arising from thin air. It comes from what is now called holography. The discovery in the late 1990s that certain gravitational theories are mathematically equivalent to quantum theories with no gravity living on a lower dimensional boundary. Juan Maldacena's work revealed this duality. In the holographic picture, gravity and space-time geometry emerge from quantum entanglement. The bulk, the higher dimensional world with gravity, is encoded in the boundary, which has no gravity at all. I remember the first time I properly understood that statement. It felt as though someone had quietly rearranged the conceptual map of physics. A region of space filled with stars, black holes, and curved geometry can, in some theories, be entirely equivalent to a system of interacting quantum particles confined to a lower dimensional surface. The geometry is not fundamental. It is an emergent description of the information contained on the boundary. Black holes sit at the center of this idea. They are the most extreme examples of space-time curvature, and yet in the holographic description they correspond to particular states of the boundary quantum theory. The interior, the region behind the event horizon, is encoded in correlations on the outside. This is what makes the recent resolution of the information paradox so compelling. The structure required to preserve information is precisely the structure that holography predicts. Another idea, often called frames, EPR, tries to capture this intuition visually. Proposed by Maldacena and Leonard Susskind, it suggests that entanglement and space-time connectivity are two sides of the same coin. ER refers to Einstein-Rosen bridges, non-traversable wormholes that appear in certain solutions of general relativity. EPR refers to entangled quantum pairs. The idea, stated in ordinary language, is that whenever two systems are entangled, there exists a kind of hidden geometric link between them. Not a tunnel you can travel through, but a representation of their quantum correlation. In this sense, space-time becomes a tapestry woven from entanglement threads. If you think back to what the page curve told us, that information eventually comes out of the black hole, the emergent space-time idea stops feeling far-fetched. For information to escape, the interior must be connected to the exterior in a subtle quantum way. The boundary between inside and outside cannot be absolute, but relativity tells us they are distinct regions of space-time. Something deeper must underlie both. The best current evidence suggests that space-time is more like a collective phenomenon than a fundamental ingredient. Much as temperature or pressure emerge from the interactions of countless molecules, the smooth geometry we experience may arise from an underlying structure of entanglement. It is not that space disappears. Rather, space might be the approximate description we use when many microscopic quantum relationships cooperate to form something continuous. When I talk to physicists working on these ideas, I'm struck by how natural the picture now seems, despite its conceptual audacity. The universe begins to resemble a vast computational structure, not in the sense of being artificial, but in the sense that its fabric is information. Geometry becomes the way large amounts of information arrange themselves. Gravity becomes the response of that geometry to changes in the underlying entanglement. And time, perhaps the strangest element of all, becomes the unfolding of correlations from one moment to the next. For someone listening late at night, perhaps trying to fall asleep, this may feel abstract, but the reason it matters is surprisingly intimate. If space-time is emergent, then the stage on which your life unfolds is not fixed, it is built. It is woven from relationships, between particles, between fields, between pieces of information, just as your own experience of the world is shaped by connections between memories, perceptions, and thoughts. Black holes, in their quiet and relentless way, force us to recognize this. They push our theories until they reveal their foundations. And through that pressure, a new idea emerges, that the universe is deeper, stranger, and more relational than we once believed. I sometimes find it useful to step back from the details of black holes and consider the wider canvas. Cosmology deals with the largest scales we can imagine, the distribution of galaxies across tens of billions of light years, the faint glow of the cosmic microwave background, and the quiet fact that the universe is expanding and cooling. These are observations rather than speculations. They trace the universe back to a hot beginning around 13.8 billion years ago. But there is a puzzle hidden in that beginning, one that has been troubling physicists for decades. It has to do with entropy, the measure of disorder. The early universe was astonishingly ordered. The best data, including measurements from the Planck satellite, show that the distribution of matter and radiation near the Big Bang was extraordinarily smooth, far smoother than you would expect from a random disordered state. That smoothness corresponds to low entropy. And here is the issue. Low entropy states are incredibly rare. A disordered universe like the one we see today, full of stars, planets and galaxies, is vastly more probable. The early universe, in contrast, was an exquisitely fine-tuned arrangement. Many physicists, including Roger Penrose, have suggested that understanding why the universe began in such a state might be the deepest question in cosmology. All of this becomes even more intriguing when placed alongside what we have learned from black holes. Their singularities, the regions where classical generals. Relativity predicts that space-time curvature becomes infinite, bear a mathematical resemblance to the singularity at the Big Bang. Both represent boundaries of Einstein's theory, places where the description breaks down and something new is required. This similarity leads to a remarkable idea, one that a handful of physicists have explored across the past few decades. It is speculative, and it should be treated as such, but it is grounded in real mathematics. The idea is this. Perhaps our universe is the interior of a black hole that formed in a larger cosmic space. To understand why anyone would take that seriously, imagine the interior of a very large black hole. Once you cross the event horizon, all paths in your future lead inward. The geometry forces you toward the singularity, not because of any physical barrier, but because the structure of space-time itself has been warped. For a sufficiently large black hole, you might drift for many hours before reaching the singularity. During that time, space around you would continue to evolve. Distances could expand or contract. Time would behave differently from the way it behaves far outside. Now compare that to our visible universe. We see galaxies rushing away from us, not because we occupy a special place, but because space itself is expanding. We also see a cosmic horizon, a boundary beyond which light has not yet reached us. No matter how fast you travel, you cannot catch up with that boundary. It recedes as the universe expands. The resemblance is striking. Inside a black hole, an infalling observer would also see a horizon permanently out of reach. The horizon would define the limits of what could be observed. Objects beyond it would remain forever inaccessible. The mathematics describing the interior of a black hole and the mathematics describing an expanding universe share these features. Of course, that doesn't mean they are literally the same, but the parallel invites a question. Could the Big Bang's singularity be related to the singularity inside a black hole? Could the extremely low entropy of the early universe be a consequence of the boundary conditions imposed by a black hole interior? Several researchers have shown that if the interior of a black hole undergoes quantum effects analogous to those we explored earlier, the same mechanisms that allow information to escape, then the interior need not end in a classical singularity. Instead, it could experience a bounce or transition, giving rise to a new expanding region of space-time. In some models, such a region resembles a universe like ours. The math is subtle, and these ideas remain hypothetical, but they are internally consistent. What I find compelling is not the claim that the universe is inside a black hole, but the perspective it invites. It encourages us to see the Big Bang not as a singular isolated event, but as part of a broader space-time structure, perhaps connected to other regions by geometries we can barely imagine. It also reframes the entropy problem. Instead of asking why the early universe began in such a low entropy state, we can ask what physical mechanism produced such conditions. A black hole interior, shaped by the gravitational collapse of some earlier structure, might naturally impose the required order. None of this replaces the standard cosmological model. The Big Bang framework remains extraordinarily successful, supported by deep observational evidence. And the idea of a cosmological black hole interior doesn't negate those observations. It simply suggests a new way to interpret them, a conceptual extension rather than a contradiction. If you look at the night sky, perhaps from a quiet place with little light pollution, you're seeing the horizon of your observable universe. Beyond that horizon, more galaxies exist. Galaxies that cannot communicate with us because the expansion of space outpaces the travel of their light. It is a horizon in a very real physical sense, and it is not so different from the horizon of a black hole. Both are boundaries of knowledge, shaped by the behavior of space-time itself. Both define what can be seen and what forever remains hidden. 105 words. Whenever I think about the story of black holes, from their 19th century origins as mathematical curiosities to their 21st century role in shaping the foundations of physics, I'm struck by how they have quietly transformed our understanding of the universe. These objects, which seem at first to be nothing more than collapsed stars, have become the lens through which we study something far deeper, the nature of reality itself. The journey begins with observation. We now have photographs of two supermassive black holes, one in the galaxy M87, another in the center of the Milky Way. Those images are not of the black holes themselves, because light cannot escape, but of the shadow cast by the event horizon on glowing gas swirling around it. What impressed me most when I first looked at those pictures was the sense of inevitability. The shapes, the distortions, the circular outline, they matched the predictions of general relativity made more than a century earlier. Space-time, it seems, behaves exactly as Einstein described, but observation alone cannot explain why. The gravitational waves detected by LIGO and Virgo give us a second window. These ripples in space-time, generated by the collisions of black holes tens of times the mass of the Sun, stretch and squeeze the fabric of the universe as they pass. Even in the quietness of a room, they shift the rate at which time flows by an amount smaller than the width of a proton. They confirm that space-time is not an abstract stage. It is a physical medium that can vibrate, flex, and carry information across millions of light years. When you place those observations alongside Hawking's discovery that black holes radiate, the picture changes again. Hawking showed that black holes are not eternal. Over immense timescales, they emit particles and gradually evaporate. And that simple fact forces a question that appears almost innocent. What happens to the information carried by the things that fall in? It is remarkable how much has grown from that one question. The modern view, supported by developments in quantum information and holography, is that information is not destroyed. Instead, it re-emerges extremely slowly in the radiation. To preserve information, space-time must be more than a smooth geometric fabric. It must store correlations. It must embed entanglement. It must have a microscopic structure. This is why black holes have become more than astronomical objects. They have become laboratories for fundamental physics. If you imagine slicing away the astrophysical details, the glowing accretion disks, the jets of plasma, the violent collisions, you are left with the essential question: how do gravity and quantum mechanics coexist? Black holes are one of the very few places in the universe where the two theories collide so directly that neither can be ignored. The idea of emergent space-time is one attempt to answer that. The best current evidence suggests that what we call space-time might arise from something deeper: networks of entanglement, patterns of information, quantum relationships woven together. Rather than being fundamental, geometry could be a large-scale description of something more primitive. Gravity could be the macroscopic consequence of how that underlying structure organizes itself. Even if this picture turns out to be incomplete, it has shifted the conversation. It suggests that the universe is not built from points in space and ticks of time, but from relationships. Connections that define structure, distance, and causality. And these relationships are not abstract. They shape everything we observe: the formation of galaxies, the collapse of stars, the behavior of black holes. One of the most evocative ideas, even if still speculative, is that our own universe could be the interior of a larger black hole. Whether this is true or not is less important than what the idea implies. It emphasizes that horizons, both cosmic and black hole horizons, are not edges. They are limits of observation shaped by the behavior of space-time. They do not tell us what lies beyond. They tell us what we can know. That perspective is strangely comforting. It means that the boundaries of our understanding are not fixed. They shift as our tools improve and our theories deepen. The Event Horizon Telescope, LIGO, Virgo, JWST, and soon the Square Kilometre Array. Each new instrument changes the size of our observable universe. Not because the universe changes, but because our horizons move outward. When I talk about these ideas late at night, often in rooms lit only by a desk lamp, with gravitational wave detectors quietly listening on the other side of the world, I find that black holes produce not fear, but clarity. They strip physics down to its essentials: information, time, and the structure of space-time. And by doing so, they offer a glimpse of something we rarely see directly: the deep foundations that make our universe possible. Reality, as revealed by black holes, is not a fixed and rigid thing. It is dynamic, relational, and profoundly interconnected. The fact that such understanding comes from studying regions where light itself cannot escape is, in a way, the most interesting part. It tells us that even the darkest places in the cosmos illuminate the nature of the world we inhabit. There's a quiet moment that often arrives at the end of a long journey through ideas like these, a moment when the complexity falls away and what remains is a sense of perspective. Black holes began, for many of us, as distant curiosities, dark regions of space we would never visit, objects that seemed to exist purely for the imagination. And yet, by following a single question, the one Stephen Hawking posed about the fate of information, we found ourselves at the edge of a deeper understanding of the universe. What I find most striking is that none of this required us to leave the world we inhabit. The answers were uncovered not by travelling to a black hole, but by listening to what light and gravity reveal as they arrive here on Earth. Photons from the centre of the Milky Way, ripples in space-time measured in quiet observatories, patterns in radiation that hint at a hidden structure beneath geometry itself. Each fragment adds to a picture that grows more coherent the longer you look at it. If you're drifting towards sleep now, it's worth noting that the story does not stop here. Gravitational waves continue to pass through the room around you, stretching and compressing space-time by amounts far too small to sense, yet real nonetheless. They are reminders that the universe is still speaking, softly, patiently, and that our task is simply to keep listening.